Welcome back everyone. In the last lecture we had seen a few of the rules of drawing root locus. We took an example and saw how we can come up with the root locus for that closed loop unity negative feedback configuration system. These were the rules that we had looked into. I am not going to again reiterate the rules, but we will be using these rules today again, but we will add a few more rules to this, and for that we will take an example which would need those few rules that I am going to introduce. Before that, let me just quickly go back to the problem that we were dealing with. Suppose you had an plant GS which has a transfer function of this form. The feedback here is unity and we have a negative feedback here. So, the open loop transfer function comes out to be G into H, which is this is the transfer function, and our idea was we will vary k from 0 to infinity and find out all the closed loop pole locations and plot it, and for that we came up with the rules that I had shown you, and we had found that the starting points will be the open loop poles, the end point will be the open loop 0. These were our breakaway and break in points, and then finally when you drew, this was one of the branches of the root locus and other branch looked something like this. So, today we will take another example and see how does this root locus will look like for that particular example. So, here is the system that we have. So, as soon as you have the closed loop system, the first thing that you should do is find out the open loop transfer function. So, the open loop transfer function in this case is given by 1 by s into s plus 3 s square plus 2s plus 2. So, this is the open loop transfer function. So, let me just reiterate. So, don't forget why are we doing this, okay? Because if we forget why we are doing this, then it will become mechanical, right? We will just learn the method and just use it. What is the meaning of that? The idea here is you have a system, okay, and that is connected in some feedback configuration. So, you have the closed loop system. So, idea here is if I change the value of k from 0 to infinity, where are the closed loop pole locations of this closed loop system? Now, in order to find that, what did we do? We saw that the closed loop pole locations are the points on the complex plane which satisfies the equation 1 plus kgh equal to 0. That was equivalent to saying that kgh must be equal to minus 1 or magnitude 1 and odd multiple of 180 degree phase. So, the points on the complex plane that satisfies the angle criteria, which is odd multiple of 180 degree and the magnitude criteria. So, basically the value of k for which magnitude of k into g into h is equal to 1 are the points which will lie on the root locus. What is the importance of these points? These are the points which you will be able to reach. Basically, these are the points where you can manipulate the system in such a way that the closed loop pole locations of the system are at those points. You change the value of k and the closed loop pole location will be exactly at the point where you wanted it to be. Why are closed loop pole locations important? Because closed loop pole locations gives you an idea of how the response would be. Remember, for a second order system, the closed loop pole location was minus zeta omega n plus minus j omega n root over of 1 minus zeta square. Zeta, omega n, all these values were related to the way the response looks. Okay, the response can have overshoots, the response can go to steady state value quickly, peak time, rise time, all the specifications we had looked into. So, by changing the location of the closed loop poles, you will be able to change the way the response of the system or the way the output of the system behaves. That is the reason we are looking to. So, basically with one diagram we already know which are the closed loop poles I will be able to manage to make the system go to. The system started with some poles, okay, which we are calling the open loop poles. Say the system started with that, but we do not want those locations, we want some other locations, because the other locations are the one which will help me to get to the desired specifications, which are MP, overshoot, peak time, settling time, all that. Okay, so that is the reason we are drawing this root locus. So don't forget why we are doing this. Fine, let me come back to the example then. So now in this example, the open loop transfer function is this. Now for this open loop transfer function, we know what are the starting points. In this case, there are poles. Open loop poles are at -1 plus minus j. So this is -1 plus j and this is -1 minus j, and the other two open loop poles are at 0 and -3. There are no open loop zeros in this case. So all the branches that will start from this point, this point, this point and this point must go to infinity. Now how will we go to infinity? All that we will see today. How many branches? Since there are 4 open loop poles, so there are 4 branches. Okay. So then comes, where will this root locus lie on the real line? On this real line, where will the root locus lie? Remember, for the root locus to lie on the real line, to its right, to any point on its right, if there are odd number of poles and zeros combined, then the root locus will lie on that point. So for example, will the root locus lie here? Yes, because if you see at this point, you look to your right, you will have 3 poles, which means there are odd number of poles, therefore root locus lies here. As a matter of fact, root locus will lie on this entire line. Okay. Will it lie at this point or any point beyond -3? No, because from -3 to -infinity, if you look to its right, there are 4 poles which is even. So therefore root locus won't lie here, neither will root locus lie here, because there are no poles and zeros to its right. So the root locus will lie between -3 and 0. So the RL lies, root locus lies between this and this on the real axis. Okay. So remember this, on the real axis it will lie between -3 and 0. On the complex it can go to different places. So at this point itself you should understand, okay, that means one branch will come out from this side and one branch will come out from this side. Since the entire root locus will be lying, so this entire thing will be a root locus. Then at some point the branches has to come out, right? And where will it go? Once it comes out, where will these branches go? These branches have to go to infinity, because there are no open loop zeros here. So these branches cannot go and terminate at some finite 0. So it has to go to infinity. It has to go to infinity. Now how will it go to infinity? In this way, in which direction will it go to infinity? We don't know that. We will have to find that by looking at the asymptotes of this example. In the same way, the root locus branches that will come out from here will also go to infinity. Now in which direction will it go to infinity? That also will again be given by the asymptote angles. So how many asymptotes we have? Since the number of poles, open loop poles are 4 here, the number of open loop zeros are 0 here. So we have 4 asymptotes. So 4 minus 0 will give us 4. So we have 4 asymptotes, and if there are 4 asymptotes, that means we will get 4 lines. So first of all, we will have to find out the centroid. The centroid is sum of the real parts of the open loop poles minus sum of the real parts of the open loop zeros, which is the 4 open loop poles I have added, and then there are no zeros. So anyways, I don't have to write that. At the end, it comes out to be minus 5 by 4. So this is the point. This is the point which is minus 5 by 4. This is the centroid. At this point, I will draw the asymptotes. Now what are the angles of the asymptotes? The angles of the asymptotes are alpha equal to plus minus 2k plus 1 into 180 degree divided by p minus j, which comes out to be plus minus 45 degree and plus minus 135 degree. So, you can place the values of k to be 0, 1, minus 1, minus 2, whatever you want to, but it has to be continuously you put it, you will get these angles only. If you increase, if you go to k equal to 5 also, it will come down to these angles only. So, you will never get more than 4 angles in this case, because basically what are we doing? We are dividing 180 degree by 4 in this case. So, we have plus minus 45 degree and plus minus 135 degree. So, you see these are the lines. So, this is your plus 45 degree, this is your minus 45 degree, and then this is your plus 135 degree, and this is your minus 135 degree. Okay. So, these are the asymptote angles. So, that means now you should understand that okay, what does it mean? This means that one branch will come from this side, one branch will come from the, at some point which is the breakaway point, they will break away, either this, they will go this side, or they will go this side, but they have to be parallel to these lines. Okay. They have to go to infinity parallel to these lines. Similarly, from here also, either this will go this side or this will go this side. Similarly, either this will go this side or it will go this side parallel to these lines. Okay. So, they will meet at infinity, it has to go parallel to these lines. Okay. So, you should have already some idea as to how it will look, but of course, still we do not have the exact plots, we have a few more points to go. So, first thing is breakaway point. Where will the points break away? Remember this is what we do, d dash ns minus n dash d equal to 0, the points at which this is satisfied may qualify as the breakaway points. So, in this case, this is the polynomial that you are getting. Now, this is a third degree polynomial. So, we have 3 roots. So, we have 3 points. Now, are all the 3 points breakaway points? For that, you have to carefully look into the points. First point is minus 2.29. So, if it is minus 2.29, it will lie somewhere around here, right. So, and we know that this point is on the root locus. So, therefore, this qualifies to be a breakaway point. Okay, this will qualify to be a breakaway point because this lies on the root locus. Now, what about these two? Minus 0.731. So, minus 0.731 will be somewhere around here, plus j 0.349. So, somewhere say here. Okay, somewhere at this point you have the minus 0.731 plus j 0.349. Similarly, somewhere at this point you have the other conjugate pair. Now, is this point a breakaway point? Now, for that you have to check whether this point lies on the root locus. How do we check whether a point lie on the root locus or not? Now, for a point to lie on the root locus, it must satisfy k, this equation, right. This is the characteristic equation, which is actually equivalent to, again I have time and again said this is the magnitude criteria and this is the angle criteria. So, it has to satisfy both these criteria. So, we will just check the angle criteria because that is the one which is important, because not all points satisfies that criteria. Now, at this point you have to check whether this satisfies the angle criteria. How do I check the angle criteria? From each of these open loop poles you draw phasors like this, and then you find out the angle. So, if this is theta 1, in this case this is theta 2, this is theta 3 and this is theta 4. So, you have to check, since these are all poles, So, minus theta 1, minus theta 2, minus theta 3, minus theta 4, if it comes to be some odd multiple of 180 degree, then we will know that this point will be on the root locus. Otherwise, it will not be on the root locus. And in this case, I have not done the calculation here, but you can go ahead and do your own calculations. You will find that this point will not be on the root locus. It will not come out to be odd multiple of 180 degree. Okay. So, which means directly now you can conclude, since minus 0.731 plus j 0.349 is not on the root locus, its conjugate will also be not on the root locus, right. So, therefore, the only breakaway point that we have is this, and this is that point minus 2.29. Okay. Now, see what happens is that some people always think that breakaway point will come out to be real numbers. No, this is not true actually. Breakaway point can be complex numbers also. So, therefore, you have to actually check whether this is a breakaway point, which means you have to check whether this lies on the root locus or not, and for which you have to go for the angle criteria. Check the angle criteria corresponding to this point. If the angle criteria gives you an odd multiple of 180 degree, then this will be a point on the root locus. Okay. So, in this case this is not. So, Fine, we are happy. We have only one breakaway point. So, the breakaway point is minus 2.29. How did I conclude that this is a breakaway point? Because I had already concluded that the root locus lies between minus 3 and 0. It has to lie between minus 3 and 0, which means minus 2.29 must be on the root locus, right? Because it is between minus 3 and 0. So, direct conclusion. Great. Now, let us move to the next point. Now, you see what happens is, this you look at this. So, we know already what will happen. This line will come like this line will come like this, and at this point they will break out, right. Now, one of the branches will go to infinity, whether this direction we will see later. Okay. So, one of the branches will go to the infinity like this, but what about these branches? These branches might go to infinity like this. Will it go to infinity like this? It may, we do not know, right. Why not? It can be parallel to this. Okay. In that case, of course, these lines will not be parallel, this will have to go like this. So, we are not sure about in which direction it will go. However, one thing is sure, that since the asymptote is going like this, we know that one of the root locus, the two branches of root locus will cut the imaginary axis. Okay. Now, what are the points at which the imaginary axis is cut? So, for this I will come to a method in the next lecture. However, for now, if you want to find out the imaginary axis intersection, so what we are trying to basically find out, what is the point at which the root locus cuts the imaginary axis. That means, at this point there will be some value of k, right, because what is root locus at the end of the day? At every point on the root locus you have some value of k. So, at this point I will have a value of k, and that when I put here, when I plug into this is the polynomial, denominator polynomial of the closed loop transfer function. So, which becomes this. So, if I plug in that value of k, the roots of this will be, at least a pair of the roots of this polynomial will be on the imaginary axis, and suppose I vary the value of k from 0 to infinity, you can find that at 8.14 it will come out to be 1.09. So, when I put 8.14 here, we will have 4 roots. Out of these 4 roots, 2 of the roots will be at plus minus 1.09. Okay. How did I find that? I will come to that soon. I will recap this example again soon, but for now just assume that, suppose that I wrote down a code where I varied the value of k from 0 to infinity, and I found that the k value is 8.14, at which the 2 of the roots are on the imaginary axis. So, these are the points of intersection of the root locus on the imaginary axis. This is j 1.09 and this is minus j 1.09. Great. Now, comes another thing. Okay. So, these are two new things. This I have not talked about in the last lecture, because in the last lecture, if you remember, the example never crossed the imaginary axis. So, I did not have to check that. Of course, I will not know beforehand whether it will cut or not, but just by, I knew already because I created the example, right. So, I knew that it will not cut the imaginary axis. So, that is why I did not give you that that rule in the last lecture. So, in this example it will cut the imaginary axis, I am giving you the rule. So, in general, when you do not know whether it will cut or not, you have to apply all the rules, go with each and every rule and find out the values. So, if it would not have cut, you would not have got a value of k. In this case it cuts, that is why you got a value of k for which the root locus cuts the imaginary axis. Now, the next thing is that you see you have a complex open loop pole here. Okay. Now, if it is a complex pole, see what can happen, the branch that will come out of this pole can come out like this, can come out like this, can come out like this. So, you do not know how is it going to come out. So, in order to find out at what angle it will depart this pole, open loop pole, we will have to find out the angle of departure of the root locus. Angle of departure means the angle at which this root locus branch will depart this pole. So, if this is how it is departing, this becomes the angle which is theta d, say. I think I have used phi d or phi p. So, this is the angle. Okay. If suppose it was departing like this, then this is the angle. Okay. In the same way, if it departs like this, then this is the angle. Okay. The convention is always anti-clockwise. So, that is what angle of departure is. Suppose there was a complex 0, then we know that the branches will terminate at this point, right. So, then we say that what will be the angle at which the root locus will arrive at the complex 0. So, those are angle of arrival. In this example, we do not have a complex finite 0. So, we do not have to talk about angle of arrival, but the idea will be similar. So, I do not have to go ahead and explain about that. Okay. So, let us find out the angle of departure. So, how do we find out the angle of departure? Let us think about it. See, this is your open loop, this is your open loop pole, right. Now, suppose there is a point near this open loop pole, which is this point, and this lies on the root locus. Now, if this lies on the root locus, we know that the phasors that will draw from these points to this and the phasor that I will draw from this open loop pole, all this angle that will be subtended would be odd multiple of 180 degree, right. This we understand, right. So, that is the idea that we will use. Now, what is the angle that is subtended at a point very near to this point? The angle will be exactly this angle only, right. A little bit here and there maybe, but not much, because the point that I am looking for is exactly near this open loop poles. So, the idea is you subtend the angles that you get from these points, okay, call them some angle. So, this is say phi 1, phi 2 and phi 3, these are the angles. So, you already know these 3 open loop poles subtend how much angle? Minus phi 1, minus phi 2 and minus phi 3. Now, the angle, now since this is done, let me just remove this. Now, so since this is the point I am looking into, very small nearby point, the angle that the phasor from this point to that nearby point must be say theta p, which must be an odd multiple of 180 degree, right. Then that point lies on the root locus, and that is what we are going to do. So, suppose there was a 0 also, then the 0 will add to, so the 0 will add to other angles, right. So, there were suppose 2 zeros, then the two zeros would also give you the angles. So, in that case, this will be the angle subtended by all the other open loop poles and zeros, and minus the angle subtended by this open loop pole 0 pole, this open loop pole must be equal to odd multiple of 180 degree. That is what we are using here. So, I will just go ahead and in this example. So, minus phi 1, minus phi 2, minus phi 3, minus phi d. Phi d is the angle of departure, must be equal to odd multiple of 180 degree, and these are angles. What is phi 1? Phi 1 is, yeah, I think I think I swapped these things. So, phi 1 is this, okay, this is phi 1, yeah, this is phi 1, this is phi 3, okay. So, phi 1 is this angle, which is 180 degree minus this angle. Phi 3 is tan inverse of 1 by 2. So, tan inverse of 1 by 2, this is phi 3, and then the angle phi 2 here is minus 90 degree, minus phi d must be equal to minus 180 degree. You can take k equal to 0 also, it is up to you. You take some value, and finally, when you solve it, you will get phi d equal to minus 71.6 degree. What is the meaning of that? The meaning of that is, if I draw this is, suppose this is 71.6 degree minus 71.6 degree. So, the root locus branch will come out like this. Now, if the root locus branch is coming out like this, then it will move like this and go to infinity. Again, when it goes to infinity, it is cutting the imaginary axis. I know already the imaginary axis point will be, intersection point will be this. So, this root locus branch will go like this and go to infinity. Similarly, it is a complex conjugate, so it will be symmetric. So, this will go like this, and then, yeah, I think, yeah, I can't make it symmetric like this. So, this will go to 0, and what about these two? These two will come like this, and then these will go to 0 like this. Okay, this is how angle of departure helps you to understand in which direction the root locus is coming out of this open loop pole. Okay, and once you know that direction, it is easier to know in which direction is the root locus going out to infinity. So, I have added these two extra additional rules now, which this one I will use something called Routh-Hurwitz method to find out. I have not yet told you about that. and these are the angle of departure. Again, let me go back to the root locus and draw it properly for you, okay, so that you don't get confused. You can draw your own as well. So take another example and try to draw on your own. So this is how it will go. Pardon my drawing. So this can be drawn with the help of this MATLAB also. Okay, and what are the other two branches? So let me take some other color. One branch will come like this, and say this is the branch which goes to infinity like this, and the other branch will also come like this, and then it will go to infinity like this. So this is the root locus for this example. So yeah, so hopefully you understand now how to draw root locus. I want you all to take a example on your own and then try to draw the root locus. The more you practice, the more intuition you will develop as to how the root locus will look like. Even if you do not get to these finer values of where will it cut the imaginary axis, what is the angle of departure, but at least if you know the shape, you will know how the closed loop systems are changing as I change the values of k to from 0 to infinity. In the next lecture, we will learn about another specification, which is one of the most important specifications which every system has to in general follow. So we will look into that, and that specification is nothing but stability. It is not even a specification, it is something that is required actually always, called stability. We will understand the notion of stability, link it up with poles and zeros, and also we will learn the method by which we can find out the points at which the root locus cuts the imaginary axis in that lecture. Thank you.